This video is for topic 7.10, reaction quotient and Le Chatelier's principle. The objective for this topic is to explain the relationship between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium. So this is where we're going to apply the principle to look at actual Q or K values. So we need to remember that if Q is less than K, so our reaction quotient Q, which is calculated the same way as our equilibrium constant. If it's less than K, it hasn't yet reached equilibrium. If it's equal to K, the system is at equilibrium. And if it is greater than K, it has moved past equilibrium and then will shift backwards in the reverse direction to reach equilibrium. So we can use whether Q is greater than, equal to, or less than K as a way to account for which direction our equilibrium will shift.
So we're going to re-examine our problem with butane and isobutane. So it's the same scenario. Equilibrium's been established in a 1 liter flask with butane with a concentration of 0.005 molar and isobutane with a concentration of 0.0125 molar. And the Kc for this equilibrium is 2.5. Then you add 0.0150 moles of butane. What are the concentrations of butane and isobutane when equilibrium is reestablished? So we already know that if we increase the concentration of butane, which is our reactant, we're going to create more product to reestablish that equilibrium. The question wants us to actually calculate what those concentrations are. So to do this, it's going to be very similar to solving for equilibrium concentrations. We just have to take into account what changes are being made. And so we're going to start by setting up our ICE table. So we have butane and we have isobutane. And our initial concentrations are 0.005 molar and 0.0125 molar. So we know the change is going to be, for butane, it's going to be our initial plus the known amount that we add to the system. And then it's going to go down because it's going to create more isobutane. So there's multiple things that are going to be happening. So we have our initial plus the amount that we add. And then we know that it's also going to go down by some amount of X. Our isobutane, we know, is just going to go up by some amount X. Okay, so at equilibrium, for our butane, we have our initial plus the amount that we added minus the amount that turns into isobutane. And for isobutane at equilibrium, we have our initial plus the new amount that is created by establishing equilibrium. Okay, so we are going to set up our equilibrium expression. So Kc equals, these are both, they're in a 1-to-1 ratio, so it's going to be 0.0125 plus X divided by 0.005 plus 0.0150 plus X. And we know, oh, not plus X, sorry. Minus X, there we go. And we know that Kc is 2.5 at this temperature. Okay, at this point, it's just our normal algebra. So I'm going to move some things around. So I end up with 0.0125 plus X equals 2.5 times 0.02 minus X. So that's my 0.015 plus my 0.005 minus X, and that's moved from the denominator over to the right side of the equation multiplied by our Kc value. I'll keep my significant figures. There we go. So then when you move everything, isolate X onto one side, you end up with X equals 0.0107 molar. You can then take this X value and we're going to plug it back into our equilibrium concentration. So if we plug in X, we end up with, for butane, 0.005 plus 0.0150 minus 0.0107, which gets us 0.0093 for our butane concentration, and our isobutane concentration becomes 0.0232 molar. And then you can plug this back into your equilibrium expression if you want to check. So we know that at equilibrium, once it's been reestablished, our Kc value should stay the same. So it should stay 2.5. So if we want to check this, we can do our products. So 0.0232 divided by our reactants, 0.0093, which is 2.5. So we've checked, we know that that works. So our equilibrium concentrations, once it's been reestablished, is 0.0093 and 0.0232, which makes sense because we know that butane should be higher than its initial, but less than the initial plus the amount that we added, because we know that some is going to go into forming isobutane, and isobutane should be higher than what we started with. So not only does it check out with our equilibrium expression, it also makes logical sense.